Good morning, gentle readers. It's December 21st, 2024. From a desk with Ross Finlayson here in Seattle, Washington. Christmas time. It'll be Christmas soon, 2024. And so that's always a special time of year. For Christianity, it's really a pretty great thing. And it helps affect to reflect on new beginnings and momentous events and such that are as well associated largely in the northern hemisphere with winter time and the depth of winter, vis-a-vis the holidays of the season, which include various holidays that last for longer times and differ in their times, like Ramadan and Hanukkah. Hanukkah starts after Christmas this year. Ramadan was last month or so. And there's also Kwanzaa is a holiday of the winter time. And then there's New Year's, and then Chinese New Year's or Lunar New Year's a month or so later. And Valentine's and Easter, and by then it's on into the springtime. But it's usually in the depth of winter, the winter solstice will be the shortest day of the year. And I seem to recall it's 21st, like today, is the shortest day of the year, or the 23rd is the shortest day of the year, according to, of course, the Earth's orbit around the sun. As with regards to its most distant points, it's considered, as with regards to that, thusly, besides that as well is the angle of the Earth, the old 23.5 degrees, and as with regards to then the oblique facing daytime at any given point on Earth, with respect to that angle particularly, not so much the distance from the Earth to the Sun, but which is largely a circular orbit, but we know since Kepler is elliptic, but yet the facing of the Earth to the Sun, and that being our star, and then we have kind of the pole star, which is Polaris, and as is discussed here when reading from star lore, that there is these various accounts of how over about 10 or 15,000 years that's changed, and yet it has actually significant influence the frames from physics and relativity with regards to frames on the larger frames, and with regards to, in the theory of physics and relativity, what's called the gravitational equivalence principle and the weak and strong gravitational equivalence principles. And as with regards to whether gravity is as an acceleration is the same thing as acceleration by means of reaction, that there are various accounts where it is so, various accounts where it is not. And when we point to Lenzethering and Parker and some of the more current experiments that help to establish that there are violations of the equivalence principle, say. And for example, I was reading an article or one of the research labs at the local U the other day, and it's like, well, that happens all the time. And so with regards to, here's a studied, the fields and the forces of the mechanic and kinetic, and then thermal and kinetic, and then mechanic and kinematic. And then as with regards to the electrical and electrostatic and electromotive and electrodynamic, and then it was with regards to the nuclear and the radio and radiation, and the electrical and the radio, which is usually that's the most common idea when you hear radio is electrical field electromagnetic waves, as with regards to antennas and the propagation and gathering of electrical waves, and amplitude modulation and frequency modulation, which make for the various effects of radio, and light, which is special here. All these being defined in terms of energy and waves, and in radiation as about the spectrum of the electromagnetic radiation, yet each as well, again, different in their own thing. It's from reading Sedov the other day about matter and fields, and that it has there's involved these kinds of energy, of course, terms of the energy and the enthalpy, and then he offers an account according to the first and second laws of thermodynamics, the first law being the conservation of energy, and the second law being a time irreversibility called entropy, as with regards to an absolute called absolute zero temperature. And so reading about that in Sedov, then in the variational principle and the virtual work principle are Lagrangian, and then the greater surrounds, say the far field type things, that Sedov is much appreciated for writing of the course, that there's the variational principle, the virtual work principle, and the energy equations, making the energy equation, virtual work equation, and the variational principle equation. Then as with regards to something along the lines of these sorts of terms, then what I was reminded was reading from Gonzalez Velasco about the Fourier analysis and the boundary value problems, is that then he's getting into Sturm-Liouville, and so Sturm-Liouville make for another count of separation of variables for in time and location for the account that's of heat in the heated bar. Then after that, when getting into the cylindrical, he says, well, then we need to get up into Sturm and Sturm-Liouville as with regards to that. It also has these sorts of terms that are much similar in the way that they're formed, is in the equation of having kind of like a main term, and then with regards to the second derivative and first and zeroth derivative, in a sense, with regards to those extra terms being kind of like the virtual work principle and the variational principle that arrive for their equations, and otherwise these surrounds, filling in the larger outlook of what is the linear, classical, rectilinear, closed system of equations when it's outward to the unlinear and for the near field and far field. And then as with regards to effects in physics of the space contraction that are real, all to be Lorentzians, establishing this kind of invariant. Another way to say that there's a conservation law is that there an invariant exists. Another way is to say that a symmetry exists. And here it's framed that those are all continuity laws, really. And so it includes those, and then as well includes issues in continuity as with regards to these doubling spaces and halving spaces, which are considered real facts of mathematics after these three continuous domains, that then thusly the space contraction what arrives at for things that are kinetic and kinematic, and with regards to the electrical field and its own particular character, and with regards to the optical and its own particular character, and with regards to the nuclear and its own particular character, and that gravity is kind of built into this nuclear force with the fall gravity idea, makes for a tetrad of quantities, reminiscent of the four elements, earth, air, fire, water, and then a fifth, a substance or an ether or a space, largely sometimes. Or the notions these days of the fundamental atomic particles of atomic chemistry called the proton, neutron, electron, and photon, representing the proton, the nuclear, and the neutron, the massy, and the photon, the optical, and the electron, the electrical. For these four sorts, a tetrad of quantities, in terms of then that there's the same sorts of fields associated with them, then as when thinking about things like the unifications of field theories called stuff like Higgs theory, or let's unify the electrical and mechanical because the optical is just kind of fleeting in flux, and so it's never really there, and the nuclear and radionuclear is like it's too slow because most things don't have any kind of effect in a long time. Although then with regards, of course, to the greater big, that being kind of like the course of science for 20 or 30 years was just like, let's reach unification and say the standard model is complete with the large hadron called the Higgs boson. And we after quark theory, so we can say that we've established symmetry violation at these energies so that they're unified in a sense. That's kind of a supersymmetric principle. The supersymmetry is just like one corner of that, and there are at least two other corners. So if there's kind of micro, macro, and meso, then for this tetrad of quantities, then there's three supersymmetries going on. And this is well known as with regards to like this hadron physics, the muon physics, and that being kind of like the usual virtual partner particles of any kind of particle model. When it has an infinitesimal gradient and shift, it's like they're superimposed. Yet according to the Wolfgang's Pauli's principle, is like they can never be in the same location. It's the idea of these particles, but at the same time, it's like when we're reading from O.W. Richardson, he establishes for two models of charged bodies when they're just slightly offset yet otherwise superimposed, that it develops a gradient through the thing. These being the kind of the muon physics, and then the neutrino physics is kind of like the ghost effects of particles that are, they pass through everything and their speed is infinite and these kinds of things. The neutrino physics. The neutrino physics are addressed as just kind of another aspect of flux. It's super classical. It's infinite reverse the other way, and tiny in a sense. Yet as well, it just affects in the greater far field all the balance of things and the continuity of things. So that goes to help show that there's more to physics sometimes, and the premier theories as well, than what's given as kind of the popular theories, because these things that I've put out there are each kind of in their own empirical milieu as so, but then trying to get them all together in the premier theories has involved the Lorentzians, that being just after Carl Neumann, that came up with, after the principles of Galilean and Newtonian theory, what became the principles of relativity theory. That relativity just means, well, it's not an absolute, it's relative. Let's work with that. That then, in terms of Lorentzian, it's figured that that's the way to do it. But then there's at least these various kinds of Lorentzians for the space contraction linear, the space contraction rotational, then special relativity instead, those being for general relativity. The special relativity has not necessarily always connected length contraction and time dilation to make space contraction, and that otherwise somehow there's always a clock hypothesis which keeps a universal time. That's not the usual summary of all the premier theories of the day, where these days there's general relativity over in one corner and quantum mechanics in another, and special relativity is used for matters of figuring out how electronic circuits work, which is why it's so central in so many things. And that the optical has things like the J.S. Bells and the aspect type experiments showing that there are these second spectrums and these things that go into making into effect the differences from each of these premier theories in terms of each other. And that there's no gravity at all, that the gravity, whether it's Newtonian or as Einsteinian and relativity is attained to in the classical limit, the Newtonian gravity, it would just be constantly doing work for nothing, and that's called a violation of conservation of energy, so it can't be. That instead here there's this simple fall of gravity from the outside, and it unites unites in the sense of having the same explanation and mechanism, not unites in the sense of erasing any difference in terms of just being energy like the Higgs theory is said to do. That the fall gravity just gets, gravity is a free theory from strong nuclear force, and then as with regards to the nuclear uncharged, well, these electrons are vanishing, vacillating, rest mass particles hard up by light speed, and they're vacillating mostly. And then today we have, that's known as, it's like the theory of electron holes is what moves the current, as those make way for waves of current through them, the carriage of the impulse, this way it's together ways to have kind of one premier theory with the best parts of the reduced in some cases, or the superimposed in some cases, parts of the premier theories, so that it can be arrived at a theory overall, at least one, that's good and doesn't contradict itself everywhere for physics, and having one of those from mathematics, because it's figured out that mathematics doesn't have any paradoxes at all. And that mathematics has at least three kinds of continuous domains, courtesy these at least three kinds of natural infinities, so that instead of having theories that and large theories like the premier theory is the entire theory, having any contradictions at all, that it's okay. And then with regards to our Platonism, that's like mathematics and numbers are perfect, and they're available to anybody. And science of that being its own thing, like the study of those. And then the idealist, then the analytical traditions, is like, well, we only have science. Science is our theory, more or less being what that is for the technical, vis-a-vis all that such other matters of the human condition, which have related the relatives and absolutes and ideals and unknowns and certainty and uncertainty for causality, and the acausal are indeterministic, as with regards to the predicativity and the impredicative, or the ambiguous after quantifiers for quantifier disambiguation. That thusly it's not so hard to put together have at least one theory of a sort that has everything in it and everything on it, and it fits all the data, so that thusly these ideas of the fall gravity and the mechanical approaches to space contraction linear and space contraction rotational and heft and all this stuff for moment and motion, and then for some of these ideas from the descriptive differential dynamics, how to kind of reseat some of the analytical developments of the derivations, because given that the foundations is kind of fixed up about continuity and infinity, then there's a lot of what were uniqueness results that can be seen as distinctness results, and so to make it so that then we can look at the whole stack of derivations after de Moivre and Euler and Gauss and Euler's identity, which makes all these things in the theories of the very small and local things, which then are expected to add up forever and everywhere. Then these ideas of the identity dimension for this singular, and then getting into the x squared plus minus 1 bit and the division left right complex and this kind of thing from the descriptive differential dynamics, has that these reflect various considerations from a look at the theory overall, and so for foundations, and then for like mathematics and logic and physics and science, the technical, that there's at least one of those, and here it's kind of as described to be kind of like so, keeping all the best things, the principled accounts of all our canon and dogma and doctrine, and reflecting upon the gift of the library that we have of all the people's works that go into it, so it's all kind of unified historical view. Then that the sum of histories, sum of potentials, least action, least gradient, those being constants and small, theory is quite perfectly profound, and as well attains to and automatically reaches then up after this account of axiomless natural deduction and axiomless geometry to Euclidean geometry, and then everything that comes from that. And then as well having the dialectic and the didactic accounts of the dialectic for this dually self-inconsistent dual monism, that here that's considered to be a pretty sound theory overall in what it's about. So today I thought to reflect on that a little bit, the Sturm-Liouville and the introduction of terms in the differential equations, the systems of differential equations, vis-a-vis matter and fields, and the energy equation, and the virtual work equation, and the variational principle, that as the terms are introduced, then they make these inner and outer products, recalling these concepts that began moment in motion after descriptive differential dynamics about a year ago, say, where moment in motion started about a year ago on Christmas. And then I recall that, and I recall it wanted to kind of figure out how to approach what is then the idea, the theory of waves, and what that means is so fungible, and how it affects how energy is reflected in this kind of sense is with regards to waves and rays, and then all the course of consideration when that exploring the theory that makes mechanics and getting around and about and turning over and the knockabout this the virtual and the fictitious and the real and the forces, all of which are real in the sense of all having import into the equation, as it were, that then having been able to arrive from that to this world's turn bit and the unlinear bit, helping establish that after the earlier readings into Einstein and showing that from a generous and thorough and one would hope so correct account of Einstein's own inputs into the theory of relativity, or his final theory of relativity, that Einstein's relativity is not the same as popular relativity, as is usually given in accounts of the theory. That thusly, to carry out part of Einstein's hope for a total field theory, that this is one, and then as regards to the unlinear, then that's helped made to say that for the Lorentzians, that there's these Galilean and Lorentzians, Fitzgeraldian and Lorentzians, Einsteinian Lorentzians, as for the general relativity electrodynamics and the optical, so that all these principles and all the derivations and all the reasoning that went into why these things are so help to explain these what otherwise are rabbit contradictions, like, well, there is an ether, there isn't. There is action at a distance, there isn't. There is gravity, there isn't. That there is, and together. So that's the usual account, and if I was just a curious student wanting to know, like, what is the theory of the physics, and according to mathematical physics, and according to science, and then according to geometry, and thusly being attached with the ideals and the absolutes of mathematical Platonism, that's what's arrived at. There are no paradoxes in it, except perhaps that there are none. There may be one, that there are none, is the idea, and then that's super scientific, which always has a place for itself. So cheers to our health, and let's see what we can find here in the stacks today. We left off with some reading from Charles Nash's Differential Topology and Quantum Field Theory. So I've been reading Tinkham's Quantum Mechanics, and as well this book a little bit, and as with regards also to the Path, Swanson's Path integral book, as with regards to the developments that go into the group theory that make for the symmetry groups and the classes, the semi-simple groups, and with regards to the associations of things and the Hermitian and the adjoint, with regards to the Hamiltonian, and then kind of opposite that, the Hermitian, with regards to the definitions that arrive, for example, co-multiplication map, by which we mean a map of the form, start quote, it is x is taken to x wedge x, or x inner x. Note that x inner x occurs in the above, or one would expect x cross x. This is to maintain our requirements for base points. And so he's established somewhere up above a way to make it so that in the inner and outer products, where the usual idea is that the inner scalar product is named a scalar product for an inner product, and it takes the product of two vectors or matrices or tensors or matroids or structures to a real value, variable's value, a scalar, meaning that a scalar quantity affects that where there's a metric and a norm that you can multiply something and it keeps it in the affine and all that through that in straight lines. So that's kind of the inner product. And the outer product is when you take two things, it's like, well, here's all the possibilities. And so here's what it takes them to be the outside form. Then there's usually just kind of the idea of the direct product, or the product. It's called multiplication in numbers, and then that takes, it results in another number, and it has all those kind of usual ideas. And then there's ideas like the cross product, which takes for something like a vector and another vector, it multiplies them as by a transformation matrix, also carrying them according to a convention within the same class of objects, vectors in this case. And the cross product happens to exist in dimensions 3 and 7 for R cubed and R to the 7th as vector spaces, linear vector spaces, within orthonormal vector bases. That these kinds of approaches then in these mathematical structures then make for being able to overload the operations of addition and multiplication and make an addition formula, or to make, according to then these terms, that then he'll be able to take an algebraic derivation that looks like all these terms that happen to have this form and write them in a briefer account, and then have that in the inner side that it shows like so. And that's useful because it's less to do, but it still has the same meaning. And then where it's not so is that any singularity theory that makes a singularity is an aspect of multiplicity theory. And so the outside, this complementary duals, has that what went into that, and the uniqueness in the individual of what then just gets reduced to a value. So the inner and outer products and the complementary duals, helping to affect on why the addition formula makes for things like the operator calculus so great, is because it makes them tractable in addition formula, or makes them tractable in lesser forms. And so that then for given products of these structures, these groups, and what mathematically, these algebras, that then they can be considered that all their products are of a kind. And that all or that some particular relation holds when the middle term, according to its left and right terms, are of a kind, or when the left and right and left have that it's commutative, it's of a kind. That then these most usual terms of the associative, the transitive, the distributive, the commutative, these laws of arithmetic, and where they do and don't hold, are then made arithmetizations of these higher level objects, that then they're just written and treated algebraically by the usual arithmetics laws. So that's an example going on here in this formula 1.24, when, as the author notes, that this occurs and it maintains our requirement. In any case, granted such a co-multiplication star, then it necessarily induces a product law, dot quote, on xy naught, where dot quote is given by this xy naught cross xy naught takes itself to xy naught. Finally, if this product on xy naught renders it a group, if it has the operations that so equip it with the members of the structure, having that also the operations happen to exist that are the same as the group operations, that it is a group, then our object is achieved, and X is called a monopique associative cohomology space, or simply a co-H space. We note also, in a similar fashion to the situation for H spaces, where X is a co-H space, then XY naught is a group for any Y. So he also introduces that when it holds, and the converse holds. And so these are the great things that make for closures, that make for operator calculus, and all the stuff that happens in function theory, and all that kind of world is as an account of these results that build it, that then make for the great strength of abstract algebra, is after all these things that go into proving that it's so, that the algebraic relations hold, then they can be just kind of forgotten, and then it's just so that all these arithmetic relations so. Helping explain why arithmetic and algebra and analysis are these three different things about each other, and that about the objects of geometry and number theory, those being kind of a geometrization is of these, an arithmetization is of these, vis-a-vis that then all these algebras, and then those being just models and reflecting other structures and models, are as of how they are, and these kinds of things. That's the language, and it makes algebraic derivations of everything, and that's when all you see is these lists and lines of formulas one after another, all each one is just an incremental transition after defining a given particular rule or mentioning the rule or just carrying it out for the algebraic derivation, why it is so derived in the formula as just these other formulas all together. Then, of course, here it's mentioned that once that is derived in, it's not necessarily closed, the algebras, but it's kind of left-leaning. Then there's the algebraic derivations that go into these things, the implicits, the parameterization, the formulation of it, with regards to these are algebraic quantities, not necessarily arithmetic quantities, nor necessarily the model's quantities, as according to all these things that go together. And that there, of course, is a particular class of those that is closed and simple, and that each one is good on its own. You can just kind of take that, any formula, and put it anywhere else and use that as the root and base of derivations or as an equation. That is kind of like so, that then in these greater accounts, then it's as of the context and the fuller context together. So sometimes equations work by themselves, and other times they're systems of equations which affect to reflect a given body of information, and then sometimes they're derivations or stacks of equations and formulas and definitions that make for, so then why there's all the assumptions that make for the implicits when things do and don't hold. So that's just kind of reflecting on this. And then we have homotopy groups. And so this gets into the whole type theory and category theory. In physics today, you'll often find category theory, because then after these kinds of algebraic derivations, then the next kind of higher structure is a diagram showing how you can get from one derivation to another. So it's just kind of like arrows connecting different kinds of relations of objects and groups by their algebras, showing how the functions between them, these arrows are called functors usually, take it from some domain to a given range and about and around she goes. And it starts and stops anywhere, and so that any time you find anything, then you can approach it in category theory as according to these ways. It's just an abstract diagrammatic format of otherwise what's just written out as algebraic derivations. Proof theory and model theory here are equi-interpretable. If there's a way to make a proof of something, there's a model theory of it. And if there's a model theory of something, that's a proof of it. Equi-interpretable. So then the author here is developing some of these things with doing to the space and some terms, which is establish some metrics and norms usually, so that then they'd be able to say that then we can make means to calculate. Homotopy groups, though simple and intuitive to describe, can be very difficult to calculate. Yes, they may. Despite the intricacy evident in the above results, there are some patterns in the values. These are known as stability properties of homotopy groups, and emerge when one considers pi sub n plus n of the s to the n for large enough n. So he's got an asymptotic result, meaning in the limit as the parameter goes to infinity, it reaches a limit. And then he's describing an emergence, and that's a technical term, after convergence, to try and figure out that that's then the part of the analysis. So that the algebra is any kind of algebra, basically just meaning for any two given elements that are related by being in the algebra, then they have these properties. Arithmetic is about numbers and the laws of numbers. And then analysis is about the completions, the asymptotic and the completions, as are discussed here. And when I say discussed here, I mean discussed here, and also part of mathematics everywhere is the usual idea. And so usually if I'll introduce something and say, well, this isn't how they necessarily do it everywhere, it's not necessarily arrived at, that this would be a common fact in the body of knowledge anywhere you go, these kinds of things would be. So that's the usual thing. More precisely, if one calculates this term for fixed m as n increases, then for n greater than equal to n plus 2, the result stabilizes, and one has, and he gives a recurrence relation. A recurrence relation is saying this term is defined by the previous term. And then there's kind of an inductive course to establish this, that it has something has to fulfill the recurrence relation. Recurrence relations are tough to figure out, but they are part of analysis built on algebra and arithmetic. Say, and then what is obtained by setting that for a value, then is able to make a cancellation. Cancellation, the greatest thing in algebra, it's like it reduces. The homotopy groups of the classical compact Lie groups G are somewhat better known than those of spheres. And so this helps reflect that then there's some conditions where there are not. So there's also a pattern in the pi G for appropriate n and g. This is a celebrated Bott periodicity, B-O-T-T, Bott periodicity. And we shall encounter it in chapter 3 when we discuss K theory. So Bott periodicity is a thing, and it's something to look at some more. To be exact, an Eilenberg-MacLane space is denoted by KGN with G a group and N a positive integer. And he talks about some invariants, and this is just this is pretty introductory material, I imagine, to get up into this sort of aspects of the field. I'm not very well studied in it. With regards to the Hurwitz isomorphism, many times I've seen the names first, and then because of formula, we'll just be using terms that are reused all the time, and so in a body of work, usually like we're going to reserve these variables, these values all the time, and then for the symbols and notations, by the time a symbol and notation is introduced, and it's the same everywhere, that then otherwise the symbols and notation are entirely ad hoc. It could be anything. But when you see somebody's kind of name associated with it, then it's kind of like, oh, now that brings into context what are these things. It talks about Riemann surface and the Hurwitz isomorphism, Hurewicz. And then he gets into one of the most important things that happens in functors is pullback. And so pullback is the idea something goes to something, and then when the contraction occurs, like, why is it not just the converse? But it is. It's just the pullback. So that goes to introduce the term a bit vaguely, loosely, but that's about as strong as it is. Talks about the tangent bundle, so it's a topology. After this, arithmetic and analysis and algebra is considered function theory and topology. So all this stuff in functors is function theory and topology. All this stuff with fibers is function theory and topology. It's all about continuum mechanics because it's really a geometrization from way up above, so that's all continuum mechanics. And then number theory is like integers, rules of arithmetic, and all that kind of stuff. Have that then this geometry and number theory for arithmetic and algebra, and then analysis. And then, although it could be seen to be like limiting cases of those, for deductive inference, then has function theory and topology. And then this operator calculus is like all this stuff that's described. It's like that catches everything else is the idea. That function theory and topology, though, are like whatever is the relation of the things. And including with regards to these things that are continuous. That's as well as it's defined. Topology and function theory. And then it's all one mathematics, but by then kind of associating these things in various ways, pretty much according to that, as the way I categorize everything, pretty much. Talks about a lifting property. And so kind of like after a pullback is a lifting. It's like, well, what happens when something, it brings along itself? And normally when you hear lifting, it's like lifting by itself. It makes for like these emergence conditions and criteria and these kinds of things. Fiber bundles, fibrations, fibers, paths and fibers. So the paths and the fibers are these sheaves, again, the connections of these fibers, and bundles of the fibers are sheaves. The loop space. And so something in the loop space reminds kind of the Zolfray metric, and these other things we discussed here. Differentiable structures for manifolds. So the idea of the manifold is that above the theory of the continuum and the continuous space, is that it's smooth and flat everywhere. And then the idea of the manifold is it's many folds. It's smooth, yet it's reticulated everywhere. So it's all the complexity of all the fabric of this space, otherwise, with regards to a manifold then being any kind of shape, any kind of surface, any kind of relation of what is, if it was pulled flat, then it would be a geometrical object, one of Euclid's elements, a continuum, which is, there's perfectly smooth continuous manifolds. A plane is a manifold, a sphere is a manifold. That then, the idea is then for stuff like this Poincare rough plane, it's like, well, it's perfectly flat and rough, and compared to Euclid, it's perfectly smooth and rough, or perfectly flat and smooth, excuse me. That then this manifold kind of starts with that, and like with the Zolfari metric, with these loops, which are not loops, strings, superstrings, which are not open and closed superstrings. The superstring theory is the same idea, that there is a continuous manifold that's reticulated, that's a plane that's reticulated, that's a continuous manifold. So the manifold in continuous manifolds, particularly, because like as Sedov addresses, like our theory is entirely continuous, and so whenever we show up with the discontinuity, that means something that's highly contrived torsional manifold, continuous yet again. Then it's with regards to how that can be and what it is, and then what happens when it lets off on either side, that's the super classical part. That means it had to instantaneously go out, or it makes its way out in waves, as it were. The turbulence, the shock, and the relaxation, all these things going into then the explanations of the dynamics of the things. So yeah, manifold is a pretty profound thing. It just means any shape, and it usually means continuous manifold. It means any shape, howsoever contrived, yet continuous. That's kind of the way it is. Classifying these spaces about the piecewise linear. It is now natural to ask, when can one straighten out a topological manifold to make it piecewise linear? And also, when can one smooth a piecewise linear manifold to make it differentiable? Both these questions can be answered using fibrations. So Nash here introduces the idea that is just kind of like, as was mentioned, there's a projection and of a perspective and a projection to a different space that takes any continuous manifold and makes it planar, not just differentiable, but planar. And then it's similar when there's the definition of the continuous domain, and it's like, well, yeah, a definition of a continuous domain includes extent, density of these points or all the fibers through it, completeness, there's no gaps, and then measure being established is that here there's some arbitrarily contrived projection to, as via the view of the lens, any given surface, any other given surface, this lens, that results a projection to a linear continuum. So that also reflects on holonomy and monodromy to make for the holographic, why it results then that these continuous manifolds are eventually so great because they can be treated at some point in time as if there's a course of passage through them, and that they are continuous and maintaining that there's all the ways of a thing. In other words, he says, a possible method for straightening out a PL manifold is now apparent. Select a topological manifold by choosing a map alpha, M goes to BTOP. Now, if we can factorize A through BPL, then M acquires a PL structure. We show this below in this diagram of these diagrams, and it just shows in this category theory, it's showing that it's taking these domains and their relations according to functions, having these defined, and with given products, establishing the relations for the more in them, and then that these other ones make for so these transforms among them that result that they're kind of the same. Then he says, in other words, the existence of the map beta of M going to BPL satisfying alpha equals pi composed beta provides M with a PL structure and is a lifting of the map alpha from the base BTOP to the total space BPL. Actually, this method does work provided dimension of M is greater than or equal to 5. See also Kirby and Siebenmann. Siebenmann. Now, I'm not sure if this Kirby is the same Kirby, Kirby, who's among people who already have one of these natural infinities called a non-standard countable infinity that's got infinity and an infinitely grand member in the infinitely many members. So Paris and Kirby are constructivists of a sort, and in set theory they make for a natural infinity that's non-standard and is countable. And that's just, I'm not sure if this is the same Kirby here, but it wouldn't be unsurprising, because often mathematicians will have to come up with something to figure out something else. They're quite considered not necessarily directly related fields, because it's all one field. So this is said to be a result found and particularly formalized this way by Kirby and Siebenmann. But who is to say that you can take any continuous manifold and relate it to any continuous manifold, and then the relation of that would as well somehow be a continuous manifold? I'm not even sure if that would always be accepted, because it would involve the singularity theory and multiplicity theory, but it's kind of a so, because there's the reverse of it. And so somehow the idea then that this torsion and the singularities in the superclassical will get involved in that, but that would as well yet remain continuum mechanics is the idea and the thing. So that wouldn't necessarily be a fact that would be given as so. And it would be a conjecture, say, or a theorem that I would make as so, but I'd probably just point to something Poincaré said. You could usually find something that Poincaré would say, or is about the hybrid geometric and the analysis that would make that so. So he talks, and this is factorization techniques and his lifting problems. And he talks about later getting into how things work up their form, and then he mentions again Kirby and Siebenmann, and about finding a non-trivials, and then with regards to an analysis that if the class vanishes that's missing, then the map B exists and furnishes M with a PL structure. And so then that's with regards to completions, how we have to arrive at it. It's like, well, there's almost all, and then there's like absolutely all. And for the inductive impasses and deductive completions, these analytical bridges, so necessary and relevant. That from reading these few pages of this book in category theory about quantum field theory with regards to differential topology, and then helping to kind of equip it with kind of the surrounds of like, well, this is stuff that is always the case. And this is the surrounds of the derivation and the interpretation of it. These are the tools as it is. That I imagine would is something that I've been trying to figure this out forever. But then this is how it's arrived at now, is being able to try and explain it in so few words. That it's not really, it hasn't really explained anything about how to read this book or what's in it, except insofar as that there is a way, and it can be the same for anybody, because it's trying to establish a proof, and so we can have a model of it, and then it's so that there is that, and then in all the theory that there is one first helps a lot, because then that's just kind of a given. In 4 dimensions, in Friedmann, F-R-E-E-D-M-A-N, Friedmann, all simply connected topological form manifolds were classified by what is known as their intersection form Q. We must define Q, little q, and this can be achieved in more than one way, from which we choose the following. In brief, Q is a certain quadratic form constructed from the cohomology of M, manifold. Take 2 elements, A and B, of H squared mz, and form their cut product, AUB and H4 MC. Then we define QAB by this, that. So this is an H, but it might as well be an R, a lot of these times. We define QAB by QAB dot A union B M. So it's just these sets, and then with regards to their intersections and what this intersection form, where A union B of M denotes the integer obtained by evaluating A union B on the generating cycle M of the topology group H4MZ of M. Poincare duality then ensures that such a form is always non-degenerate over Z, and so has determinant Q equals minus plus 1. Q is then called unimodular. Also, we refer to Q as even if all its diagonal entries are even and is odd otherwise. The result of Friedmann leads to the following. So, with regards to that in Poincare duality, that's not necessarily what I intend to convey by Poincare completeness in a sense, because that's instead kind of like, well, you can forget that it's not necessarily so that what you'd have to arrive at completeness. Instead, you can just say that some of these other parts drop out. So that makes it sensible, fungible, and tractable, and also it's easier to prove. Whereas at the same time, there's this abstract outside, this like, well, it always exists, and so if you can reach completion, that's considered perfect. As with regards to these, it's like we're following a course, we're without loss of generality, well, except a little bit, we're keeping this together this way, and its generality that is like to so. This is a very powerful result. Friedmann's is a very powerful result. An illustration of the impressive nature is rather easy to provide. So it sets up some isomorphisms and homeomorphisms vis-a-vis the diffeomorphisms. Shape, the morphisms, the shapes. Friedmann's result says that for a simply connected manifold, here M is always means a manifold with even intersection Q, there's only one homeomorphism class for M. Therefore, S4H is homeomorphic to S4, and we have established the conjecture. So inside, at least, this otherwise thing, they've figured out a way via a Poincare duality to make a Poincare completion, in a sense. Incidentally, this means that the Poincare conjecture has now been proved for all n except n equals 3, the case originally proposed by Poincare. So then that's what we to get to is the Poincare conjecture, and these being the matters of these sorts of completions. And here, I'm more interested in having it without complex numbers, really, and to keep it real valued. And kind of like after, Lefschetz and for analytic geometry and the geometer's sake, that it's kind of considered contrived, the complex analysis, when it's somehow supposed to be real. So for that, we need this super classical real, non-standard real analytical character bit to arrive at then these things that having those kinds of tools it's the same mountain, but it's just kind of a different approach that's considered upside down and thus impassable, but somehow there's arrived at something of an analytical bridges, these inductive impasses of the chasms of the glaciers of the approaches to the mountain. This one mentions Fried and Uhlenbeck, Yang-Mills, Donaldson's Euclidean Yang-Mills actions, instantons, solitons, and instantons. The unimodular. A final word about non-compact manifolds. There is a result due to Quinn, which says that non-compact manifolds are always smoothable. However, if we choose m equals r to the n, then for n not equals 4, there's only one smooth structure, but for n equals 4, there's an exotic differentiable structure on R4, i.e. there exists a smooth R4, which is homeomorphic but not diffeomorphic to the standard R4. This is a consequence of Friedmann's and Donaldson's work, cf. Gompf, GOMPF, and Fried, FREED, and Uhlenbeck, UHLENBECK. An exotic R4 is referred to as a fake R4. It is now known, Gompf, that there is a continuum of exotic differentiable structures that can be placed on R4. This is in sharp contrast to the finite discrete number of exotic structures that arise in the use of obstruction theory with compact manifolds. It is clear that this section shows that 4 dimensions is special in very many ways, and that as yet much remains to be understood. A useful reference is Kirby 1. Kirby. Here Nash references Kirby as The topology of four manifolds, Springer Verlag, Kirby, R.C., 1989. So that helps goes to show that in this very high level work, then they kind of arrive at all these things which are just matters of perspective and projection for the geometry as motion. But here it's like, well, after an identity dimension, then it's working up and out. We got Descartes and we got Euclid, and they're going along just great. Then we also have the hypergeometric that kind of lives there, and then we're able to take these ideas of Poincaré and Euclid and put them together, and that it necessitates having the superclassical continuum mechanics and continuum dynamics from underneath. So luckily that's not already entirely contradictory to the usual fundamental account, because infinity and continuity are not just they're central and primary, and that's a great sort of approach to the mathematics and all. Let's see here. So there's that, and that's a nice kind of reading, you know. It's helping to extract something that's pretty high level. It's like, well, it's completely fundamental. And then this was Sedov again, and he edits this work. There was this, not Zilronovich or Alexeyev, Siebenmann, canonical equations of neutrino fields and waves. So this is the superclassical flux part, which happens on the outside. The neutrinos are arbitrarily small. They're fleeting in flux. Light is kind of a particular example of like the biggest neutrinos. But then light's, in the theory these days, has a second spectrum of photons and photinos and all these kinds of things. And all the different particles have their enos, which are like the tiny opposite particle going the other way, infinitely fast. That, and our Siebenmann, Sibgatulin, a doctor of science in physics and mathematics from the M.F. Lomonosov Moscow State University. He says, or in translation it said, this work is devoted to the interaction of sourceless gravitational and neutrino fields within the scope of general relativity. The stress is on the properties of these fields when an abelian commutative group of motions, G on V, is present. In this case, it becomes possible to reduce the Maxwell-Einstein-Weyl set of equations for interacting sourceless gravitational, neutrino, and electromagnetic fields to a set of canonical equations. So this would be definitely required for this part of the theory, I'd imagine. In section 7.1, these equations are derived for the cases of stationary axisymmetric fields and plane waves. Section 7.2 makes clear that the equations derived in section 7.1 possess remarkable group properties. First, we show that for a denumerable set of infinitesimal solutions, there exists an infinite dimensional algebra, a hypercube. The algebra is then exponentiated and brought into the form of an infinite set of linear algebraic equations, which proves to be equivalent to a matrix integral equation. We then build an exact solution for any type of neutrino field, which may serve as a starting point for obtaining other types of solutions. Well, that's great. I'll be looking to read this a little bit more. Let's see kind of if I read this canonical equations of neutrino fields. For zero rest mass, as the reader must know, the Dirac equation for a spinor field breaks up into two independent equations, the Weyl equations, describing neutrino fields. Let us assume the space is filled by sourceless electromagnetic and neutrino fields, which bring about gravitational fields, the neutrino electromagnetic vacuum. The total set of equations describing this vacuum consists of the Einstein equations with the energy momentum tensor of the neutrino electromagnetic fields and the Weyl and Maxwell equations in vacuum. Well, I'll go to look at this a bit more, and it gets up in the usual ideas of killing vectors, K-I-L-L-I-N-G, Neumann and Penrose, about their projections, about the above tetrad field, where we have a tetrad field, a complex tetrad, and by agreement do not depend on time t or angle phi. So it's like, as long as you don't really need a metric or norm or the affine or the Lagrangian, that then I'll just kind of leave off from reading that, because then this is being set up as sort of a framework and a model of constitutive equations, or the canonical equations as it's put for these fields, but then to figure out how to make it when it's not time invariant, or then when it is time invariant, and with regards to the energy instead of the momentum, as with regards to the energy momentum tensor, defining the tensors, these kinds of things. That this is a pretty great little thing, and then also that it doesn't really have gravity perhaps, but it is all about Maxwell's fields is really what it's about, and then Weyl's equations after that, and then Kinnersley is mentioned again, and Einstein as with regards to Einstein's equations and the form of them here with regards to grad and thusly Green's and Stokes and that, that's how it's built with regards to the tensors. And then I'd well be advised to consider some more from Ogan about this kind of thing with regards to these kinds of things. A symmetric second-rank tensor. It's like, well, what are the tensors? If we calculate the energy momentum tensor of the electromagnetic field and substitute the result in, we get this. To obtain a closed set of equations. Next, we reintroduce the variables x and t. This is the space and the time. By the formulas, according to u equals x plus t over root 2. And v equals x minus t over root 2. So you got like an x squared plus minus y one bit, and then over root 2 with regard to the quadratic. So then that gets into the whole triangle law and all that stuff that goes into the metric and norm and all the usual fundamental things. All the usual things. The very few, all the usual things. Well, gentle readers, good day. I shall so hope it's a happy holidays. So happy holidays and Merry Christmas. And I hope this has been useful today to kind of arrive at this, like, there's an overall theory of mathematics and physics. It's great. Hey, so long.